Today's webinar is going to be on modeling consolidation of slurries, a water balance approach, and the presentation is given by Nicholas Brink with Stantec, who has graciously volunteered to present this for us. And I think this is a really great opportunity to see someone that is actually in the trenches using GoldSim and see how it's being applied in a real-world application. So I'm really excited to see this. I feel like I'm going to learn a lot from this, and based on what I've seen, I think it's going to be a really good presentation. So thank you for joining. I think this will be a good experience for all of us. And so I'd just like to introduce Nicholas Brink. Thank you, Nick, for taking the time to prepare this and do this presentation. Just so all of you know, if this is the first time you've used GoToWebinar, there's a dashboard there. Obviously, you can see it. There's a handout that I've uploaded, and that will be used, something that you can look at during the presentation. You just click on it to download it. Also, if you have any questions, you can click on the hand button that you see there. That will notify us, and then you can type in a question in chat there. Nobody has audio enabled, so you just have to type in the question with chat. And Nick will take your questions at the end, or or maybe during, but usually we take questions at the end. So you just can just be patient for that. And if you do have any problems hearing or seeing the screen, also do please let us know. So I'll go ahead and turn the time over now to Nick.
All right, well, great. Thank you again, Jason. We really appreciate this opportunity as well. I've been looking forward to this. And so, yeah, as Jason said, my name is Nick Brink with Stantec. I'm a geotechnical engineer in our mining group, and I've been using GoldSim to do water balance modeling and to some degree consolidation modeling for probably about 6 years or so. And it's also the topic of my master's thesis, so it's definitely a topic that I've been interested in for a long time, and I'm excited to share it with you today. So without further ado, we'll move forward. All right, so today's agenda, I'm going to start with a brief deck of slides, and so hopefully this will go quick, and then we'll jump into the model. The purpose of these slides is really just to get everybody on the same page when we're talking about consolidation. There's a lot of different terms and terminology out there, and this will just help us kind of all get on the same page so that we have a foundation that we can build on together when we go to build a model. But first, I'm going to start with a safety moment. That's something that Stantec starts every meeting with, and something that I'd like to carry through here. And then we'll move into some consolidation theory. As it says here, don't worry, we're going to keep it simple. This is supposed to be a high-level overview and not necessarily a lecture in consolidation. So I'm assuming that you've been exposed in one form or another to some of the basics of consolidation, even if it's only, you know, just tertiary. That's fine. And so we're going to go through some of those basics, talk real briefly about some of the lab testing that might be needed, and then talk about how we're going to model slurry consolidation. And so as the title of this the title of this presentation indicates, the focus and ultimately the goal of this is to discuss how this influences a water balance. And we're going to use a mine tailings dam as sort of an analog for the rest of this webinar. Although the principles that we discuss here today are going to be applicable to pretty much any kind of slurry that you might be encountering. And again, as the abstract indicated, that could be a wide variety of things. So for a safety moment, it is now springtime, and I think I saw there's a few people calling in from out of the United States. So within the United States, it's springtime. Those calling in from South America may not be the case, but for us up here it is. And so that means that bikers are on the road, and that means that motorists and bikers alike have responsibility to keep each other safe. So bikers, it's your responsibility to use caution around intersections and to use the appropriate hand signals at all times. And if you're not sure what those hand signals are, it's important to look them up. Then motorists, it's your responsibility to keep your eyes open for bicyclists. We are in an area where, you know, it's our responsibility to share the road. And so motorists, it's also convenient to know these biking hand signals. That way, if someone gives you a signal, you'll know what they're trying to indicate. And so ultimately, it's everybody's responsibility to keep everybody safe on the road. And so that's our safety moment for today. Next, we're going to jump into a quick discussion of consolidation theory. And again, as I mentioned before, we're going to try and keep this pretty high level. So if you're not familiar at all with consolidation, here's a simple working definition. When a load is applied to a saturated soil, that soil undergoes some kind of volumetric strain. And that happens because some of the pore water is being expelled. So that's basically consolidation. If you're not familiar with this phase diagram that's shown on the screen, this is just a convenient way to show the breakdown between solids and voids within a soil. So down at the bottom of the screen, you can see an example of, just what a little section of soil might look like in this state. And that phase diagram above it simply just represents that soil, right? So we have a certain volume of voids, and we have a certain volume of strictly solid particles. And the combination of the two gives us our total soil volume. So this is convenient to use to show what consolidation looks like. When we apply a load, the void volume decreases, and some of that water within the voids is expelled. Now, a key assumption here is that our solids are incompressible. That means the only change in volume that happens in the soil, it's happening because the void volume is being reduced and because water is being expelled. In terms of our water balance, that's a key point, okay? Because now we can say that whatever change in volume occurs in the soil, that's also the amount of water that we're going to see available from that soil. Now we have three simple relationships shown off to the right. These relationships are just simple ways to represent the phase state of our soil. So in other words, each one of these three relationships, the void ratio, the dry density, and the solids content, they change with consolidation. And so we can use them to indicate the state of our soil during consolidation. And now, just as Jason mentioned, this slide is actually the handout that Jason was talking about. And we will refer back to this briefly in the future. So if you haven't yet downloaded it, I encourage you to do so. All right, so how do we represent consolidation? Ultimately, consolidation can be broken down into a load-dependent component and a time-dependent component. All right, so these are two key points. Classical consolidation theory, we assume a constant permeability. So this plot on the bottom right, we see what classical consolidation theory would assume. So if you're familiar with an odometer test, with Terzaghis consolidation calculations, things like that, these are the types of consolidation calculations that would be used for, let's say, settlement beneath a footing of a foundation or something along those lines. And for those types of calculations where the change in void ratio is relatively small, in other words, very relatively small volumetric changes or strains, that assumption is valid. But when we're talking about a slurry, the slurry is going to undergo significant change in volume. And because of that, we have to account for the fact that our permeability is changing with our change in void ratio. All right, so that permeability is what controls the rate of volume change. In other words, if we have a sand with real high permeability, then the consolidation could occur almost instantaneously. If we have, let's say, a clay that has very low permeability, that's going to impede the water as it tries to escape from the soil, and it's going to slow it down. And so that consolidation under a constant load could take days, weeks, even years, potentially even centuries, depending on the situation. So when we're looking at this, we have to understand that, first of all, consolidation is not just load dependent, but it's also time dependent. And now the compressibility curve shown on the left, this is what controls the magnitude of the volume change. So we've got permeability affecting the rate of consolidation. We've got compressibility that affects the magnitude of the volume change. All right, so these two things hopefully kind of make sense. I'll pause here in a few moments to take some questions, but for right now, I'm going to move on and wait. If you could give me just another 5, maybe 10 minutes. So to get these curves that we just looked at, we basically need to do some lab testing. These curves are essentially material-specific properties. And because of that, we need to evaluate those properties for each material. So on the left, you see a classical odometer test setup. this might be something you've seen in the past. And this is used for typical small strain applications and for less compressible materials. They can be used to test slurries. It's just difficult, and it requires some special non-standard setup. Then what you see on the right, though, this is a seepage-induced consolidation test, and this is the test of preference for a slurry. This, or there's other similar tests available out there. But ultimately, the seepage-induced consolidation test allows us to probe the material at very low effective stresses. So I'm going to flip back a slide. Notice this compressibility curve on the bottom left. At a low effective stress of around 1 kPa to 10 kPa, kind of in that range, we're seeing a fairly significant change in volume from a void ratio of 2.6 down to 2.2 approximately. And so that significant volume change would be very difficult to capture using an odometer test or a standard classical consolidation test. The seepage-induced consolidation test applies very small loads across a soil specimen using actually just water flow. So it's a seepage-induced stress. And by doing that, we can evaluate our compressibility at low effective stresses. For a slurry, that's important because in an extremely large impoundment, capturing the volume change at these low stresses could have a fairly large impact on our overall calculation results. Okay, so the second thing that the seepage-induced consolidation test does is it directly measures the permeability during the test. So we can evaluate this relationship between permeability and void ratio. All right, so once we have our material properties, the next thing we need to define is our impoundment. So in other words, the facility in which we're going to store this slurry. All right, the easiest way to represent the impoundment is through a stage storage curve, which is what's shown on the bottom right. And if you're not familiar with this, it's a fairly simple thing. This diagram on the bottom left is showing basically how a stage storage curve is developed. For every elevation of slurry, we would be able to calculate the total volume of slurry within that impoundment, and that represents 1 point on the curve that you see to the right. So we do this several times over, in the case of this curve a few dozen times, and that's how we produce this curve. So this curve represents the geometry of our impoundment. And although I'm not showing it here, we could also do the same thing with surface area. And that becomes more important for the water balance calculation, which we'll do later on. So once we have all of this information, we have our material properties, we have our impoundment geometry, now we need to understand how is the material behaving once it is deposited. In other words, how is it consolidating? So this is a more difficult question because especially if we're talking about a continuously deposited slurry, right? So in this case, if we look at each individual element of soil within our impoundment, each element of soil is under its own unique state. I'm just going to call it a general state. And because of that, we'd have to look at each element individually. So specifically, each element is under its own unique effective stress. It exists at its own unique density based on that state of stress and based on how much it's consolidated already. And it also has a unique drainage path. So the water escaping from that little soil element might have to travel through 10 more elements or 10 million more elements to get to the surface or to get to some point where it can drain freely. So how do we handle this situation? Well, ultimately, we need some kind of a numerical method to help us out. And that's what's shown down at the bottom of the screen here. This is we call it a pseudo three-dimensional numerical model. Really, what we do is we break up the impoundment into a series of columns and then perform one-dimensional consolidation numerical modeling on each one of these columns. And we fill these columns, numerically in such a way that it represents the actual process of filling. So the difficult thing here with continuous filling, if you're familiar with numerical modeling, is that your mesh is constantly changing and not just deforming, but you're actually constantly adding new elements to your mesh. So this is something that requires special attention and special codes. So there's a few codes that are dedicated to do exactly this one-dimensional consolidation modeling. Examples would be FS Console and Condis, and we typically use Condis. We found that it tends to be more accurate. And now there's also the ability to do things like a three-dimensional Plaxis model or a three-dimensional FLAC model. And that can certainly be done in situations where the three-dimensional effects are significant. But for most of our calculation purposes, and really with the end goal of the water balance being in mind, this tends to be, you know, perfectly adequate. We don't need to go in any more detail than this. All right, so there was a quick and hopefully not too painful intro into some consolidation basics. So I'm going to pause real quick to answer a couple of questions. All right, so sorry, I'm just reading a question here. It says, once questions begin, might be helpful to discuss the controlling size fraction on permeability. That is, examples given of clay versus sand, but discuss proportionally how much clay mixed in sand makes the mixture act more like a clay. Okay, yeah, well, that is an excellent question. And really, you know, this permeability curve that we showed, that is very much a material specific item. It's a material specific property, right? So like I mentioned before, if we have a sand with, let's say, a clean sand, I mean, potentially, you know, an ASTM C33 kind of sand, very strictly controlled, that sand is going to have a higher permeability than something that has a silt or a clay mixed in with it, just as this person was asking about. So the question was, how much clay, I think, if I'm kind of reading between the lines, how much clay does it take for this material to begin to act like a clay? And again, it's material specific, so it requires some testing, but it doesn't take all that much. I mean, you can see 15 to 20% fines, clay fines that is, start to really affect both the compressibility and the permeability of that soil. But right, I think the most appropriate answer is simply that it's material specific and it's going to require some lab testing. So I hope that helps. All right. All right, so with that, let's move on. So let's start talking now about how we're going to incorporate consolidation into our water balance. There we go. Now, as we mentioned, these numerical models have the ability to represent elements of soil, right? And they're able to represent lots and lots of elements of soil. So they can break our impoundment down into lots of discrete elements. And although that can be advantageous, it can also be very difficult to use in practice. So within GoldSim or within any other kind of water balance model, it's more appropriate to try and represent the impoundment as a whole. And we do that with an average impoundment density curve, which is what's shown at the right. So this curve represents the average density of the impounded material over time. And this impoundment curve, it accounts for the fact that we're constantly depositing new slurry, and it also accounts for the fact, or the geometry of our impoundment. It accounts for the material properties of our slurry, and it accounts for the drainage conditions within the impoundment. That's something I haven't really mentioned before, but just another point to make if there's some kind of a substrate that's significantly more permeable. So this density curve that we're seeing here is how we're going to represent consolidation in our water balance models. And you can see I've got two curves shown. One is for a deposition rate of about 100,000 tons per day, and one for a deposition rate of 150,000 tons per day. So you can see there's a noticeable difference here. So the deposition rate is one thing that affects these curves, but also the impoundment geometry. So and these other things that are listed here on the slide. Really, the key point is these curves are highly dependent on the deposition situation that you're looking at. So if you develop a curve using a numerical model like these, but then go into your water balance model and change the deposition rate, or really it has more to do with the rate of rise in the impoundment. If you change these things, really you should be looking at whether or not you need to change this density curve. If it's a small change, then right, probably the density curve is not going to be changed enough to need to worry about doing a whole new numerical model. But if it's a substantial change, like you see here, there can actually be a fairly substantial difference. And so that's something to keep in mind. Now, moving on to just a general schematic of a water balance. Let's see how consolidation fits into our calculations. So first of all, a water balance on the most basic level is really nothing more than addition and subtraction, right? We have our inflows that we estimate, we have our losses that we estimate, and the amount of water that we have available for reclaim is just simply the difference between them. You may have to consider change in storage of a reclaim pond or something along those lines, but ultimately it's simple addition and subtraction. Now, calculating these flows could be a little bit more difficult, but that's something that we'll leave for another day, I think. So how does consolidation fit into this? Well, it fits in terms of our entrainment loss. All right, so this is a little bit counterintuitive. Previously in this phase diagram in your handout, I was showing that consolidation leads to expulsion of pore water. And I think a lot of people are probably curious about how you calculate that volume of water expelled from your soil or from your slurry. Well, I would submit, and this is the process that we use at Stantec, it's actually simpler to calculate the amount of water that stays within the slurry. And then based on this difference of inflows and losses, the amount of water that's released is going to be implicitly accounted for. So that's our preferred method for performing these water balance models and dealing with consolidation within those models. Okay. So our next step is going to be to jump into a model. I'm going to pause again and take a look here, see if we have any questions. Okay, we have a question. How is the density curve established? Okay, good question. Maybe I didn't discuss this quite in enough detail. This density curve is established based on our numerical model. Okay, so our numerical model brings in material properties, deposition rates, things along those lines. The numerical model is going to give us an output, which is essentially just the density of our impoundment with time. All right, so the numerical model tracks the density of every element of slurry within our impoundment. This density curve basically just represents the average of the densities of each individual element of soil. Okay, so that's how this density curve is established. And with these numerical codes like FS Consol, Condis, and others that are out there, these density curves are a direct output. So you'll input material properties, you'll input a stage storage curve, you'll input a deposition rate, or really a rate of rise, and you'll input drainage conditions for your impoundment. And the output from that analysis will directly be this curve. Now, if you're using FLAC or some of these other more advanced codes, then you'll have to convert from element level densities to an average impoundment density. All right, so thanks for that question. For the sake of time, I'm going to go ahead and move on. I hope that's answered, but if not, feel free to reach out to me by email, or at the end, if we have time, feel free to bring this question up again. All right. So with that, we are ready to move over to our GoldSim model. And now, for the sake of this exercise, I'm assuming that everybody has had some exposure to GoldSim. So I'm not going to go through, element by element and try to explain everything that's going on, but I'll make some notes along the way here to try and help everybody out. And now I'm going to try and switch my cursor over so it's easier to see. And please feel free to either raise your hand or ask a question. I'll be able to keep an eye on it more closely now that I'm in GoldSim. If you can't see anything, or if I need to zoom in on something, please feel free to ask. All right, so here's GoldSim. We have several elements that are already in place here. So I've taken the liberty of setting up some of the basics of this model already, again, just for the sake of time. I'll first show you what I've done just for the setup of the model itself. Okay. Sorry, everybody. I think my cursor I actually will not be able to use that highlighted cursor, it looks like. There we go. So I've hit F2 on my keyboard. This brings up simulation settings. A few quick things. We're going to run this simulation for a period of 30 years. We're going to use the elapsed time mode. And so this just allows us to start from time 0 and count upwards in days or years or what have you. There are options to switch to a calendar time mode, but for the sake of simplicity, we're just going to keep it elapsed. And we're going to set up a time step of 1 day. Now, for the model that we're creating today, the time step of 1 day is probably a little finer than what we would need. However, most of the time doing these models, I prefer a time step of 1 day, simply because it allows us to get better resolution around the timing of, let's say, an impoundment reaching capacity or changes in deposition rate, things of that nature. So this time step of 1 day is something that I recommend that we would use going forward. And so that's what I've done. And I'll bring up something else as well. There's also this option to use these global properties. I've not done this. In the past I have though, and they're very handy. Now for the sake of today, I've actually just brought some of these global properties, things like density of water, specific gravity of solids, percent solids of our whole tailing, things like that are just constants in our model. I brought those in as data elements. And so I've done that just so that it's easier to see in the model, but just wanted to highlight the fact that you could do it this way. And in fact, it's pretty slick if you do it that way. All right, so the next item to look at is the fact that I've brought in some other inputs already. So up at the top here, I usually like to set up my models with supporting information up at the top. So this is any kind of just a generic input that's going to be read into the rest of our calculations. I've brought in our density curves. These are those 2 curves that we looked at in the PowerPoint slides. And I've also set up a constant density. We'll see if we have time. We'll run this model in a couple of modes to see the difference between constant density and then bringing in our actual consolidation calculations. We've brought in the impoundment geometry in terms of our elevation volume curve. And again, this is the curve that was shown in that PowerPoint slide. And then we've brought in just a maximum impoundment height. This is just a static value that we'll use to evaluate when our impoundment reaches capacity. All right, so I've set these elements up ahead of time just so that we can quickly walk through them and not spend a whole lot of time on the material balance. But a point that I do want to make is that before you start working on a water balance, it's always first important to understand the material balance. So the first step in any kind of water balance modeling is to understand how your solids are being routed and how they're behaving. All right, so if we look back at that phase diagram in your handout, right, we're dealing with just that lower portion, that brown solids portion. So I've set up an input here that represents, in this case, our concentrator production. Ultimately, this is just the rate of deposition of our tailing slurry. All right, that comes into an integrator element. This just sums up the total amount of tailing that's come into our impoundment throughout, up until the current time step. And then we use that to calculate the volume of our impounded tailing, and that's done based on our density. So I've used a selector element here as well as an input element to pick between our densities. We can use the density curve for 100,000 tons per day, for 150,000 tons per day, or we can select constant density. If I select this little selector element, or excuse me, this input element, here's some instructions down here in our notes view. That's how we're going to use this density selector within our selector element to pick which density curve we're going to use. So at this point, it's a little bit manual. Over here, we've got an input of 100,000 tons per day production. So we want to make sure that we're using the density curve associated with that. And I've got a value of 1 selected there. And so we should be getting the right density curve. Now, some other things that are usually important for a material balance are to evaluate the height of the slurry, really the height in this case of the tailing beach, as well as the rate of rise. So the rate of rise is important for embankment dam construction if it's a continuously constructed dam, because if the rate of rise gets too high, then it becomes difficult, if not impossible, to maintain the dam and continue constructing it ahead of the impoundment. So that's something that we look at often in a material balance. And then this milestone element, this is just used to indicate whether or not our impoundment reaches its ultimate capacity. All right, so that's all I'm going to say really about these calculations. Feel free to look at these in more detail later on, and perhaps at the end of this we'll have time to. But I think for now, we'll leave it there. And we'll go ahead and get started with our water balance now, since that is certainly the focus of our talk today. And so I've already burned through 30 minutes, and I apologize that we're not spending more time within GoldSim. But I will say this, the reason is that it's important to understand these background basics of consolidation before you try and bring things into GoldSim. It's easy to pick a density curve, apply it in GoldSim, and assume that your calculations are correct. But the reason for that introduction is that it is actually quite important that we get the right density curve to use in GoldSim, right? So our consolidation calculations start long before we ever touch GoldSim. But with that said, let's move forward and let's start building our water balance. So just as I showed in these PowerPoint slides, I'm just going to flip back to that quickly. Well, let's see, I'm going to flip forward. And I'd like to just show again this little schematic. All right, so this schematic shows us our losses, our inflows, and ultimately a simple way to calculate water available from reclaim. These calculations can certainly get more complicated than this, but for the sake of this demonstration, we're just going to stick with something that is just this simple, and possibly even more simple. I think for now, we should just assume there's no precipitation. In other words, we're going to assume that it's an arid climate, dry climate, with precipitation that is, compared to the amount of water coming in with slurry, very small. And we'll also assume that this foundation wetting loss is 0. So that being said, our only losses are going to be evaporation and entrainment, and our inflow is just going to be water coming in with the slurry. So that's only 3 things that we've got to calculate, and that'll make it a little bit simpler for us. And then we will estimate the amount of available reclaim based on these calculations. All right, so back to GoldSim. Now that we have our material balance set up and we're tracking the progress of our solids in our model, now we can set up the calculations for tracking the water itself. So let's start by looking at the amount of water that's entrained in our tailing slurry. So down below, I've got some more supporting information. These are just material properties, climate information, things of that nature. These are constants. And again, I brought these in ahead of time just to make things a little bit faster for us today. One thing I have not talked about yet, though, is the specific gravity of solids. If you're not familiar with the term, it's essentially just the ratio of the density of the solids to the density of water. So it's just a measure of the density of the individual solid particles themselves. And in geotechnical engineering, that's something that we use quite often. And it's sometimes represented by something other than GS, just FYI, it's still the same thing. Solids content we've talked about. Density of water I've brought in is just 1 gram per cubic centimeter, just the basic density of water. All right, and down below here, I've also included a couple of equations that are going to help us as we make these calculations. So let's get started. The first thing we're going to calculate, like I said, is the amount of water entrained in our inflow slurry. To do that, we'll use an expression element. We're going to call this water in whole tailing. So when I refer to whole tailing, really I'm just referring to this slurry that's coming in, but in a state prior to it being deposited. So this is essentially the amount of water in a slurry that's being piped down from our concentrator facility in this case. We're going to give this a volumetric flow rate set of units, liters per second in this case. So I apologize if everybody is used to imperial units. A lot of what we do is metric, and so I'm going to stick with metric units for today to avoid making public mistakes. But I will point out a very important aspect of GoldSim here, which is that even though I'm using, say, SI units here, I could easily define this equation by referencing constants or other elements that use imperial units, or that instead of liters per second, use cubic meters per day or something like that. And because GoldSim is dimensionally aware, the conversion between units happens behind the scene. So we can define anything we want in terms of units, and they will automatically be converted so that the calculations happen correctly. This is a very, very helpful aspect of GoldSim. I don't know how many times I've made mistakes in Excel trying to run a water balance, and I forgot to convert from cubic meters to liters or something along those lines. So that's something that helps us avoid some mistakes. All right, so this calculation is based on this first equation down below. Our mass of water is equal to the mass of solids divided by solids content minus the mass of solids. That equation is based purely on the relationships shown on your handout. So I won't take the time to solve it, but if you look at your handout, you could solve it yourself for this equation. All right, so I'm going to input this equation. Our mass of solids, that, let me find the element name, I've forgotten, MS. So our concentrator production, that represents the rate of our solids masses coming into our impoundment. And actually, let me back out again and I'll get this equation visible. All right, so our equation is going to be mass of solids divided by solids content and subtract out again mass of solids. But our GoldSim element is giving us an error. It's saying units do not match up. The reason is that we've got a volumetric rate is our display unit. We've got a mass rate in this equation. So mass in terms of metric tons is what this equation is calculating, right? So we're going to convert from that mass over to a volume by dividing by density. Since we're dealing with water, it's simply just the density of water. So take this entire expression and divide by density of water. And again, density of water, that's one of those elements that I brought in ahead of time. And I defined it as just 1 gram per cubic centimeter, as you see here. All right, and that's it. This now represents the total volumetric rate of water coming into our impoundment along with our slurry. So since we're going to assume 0 precipitation, now the next step is going to be to estimate our losses. And as we mentioned just a few moments ago, we're going to assume 2 losses, entrainment and evaporation. So the entrainment loss, this is where we are going to account for the consolidation properties that we computed previously, right? So we're going to bring in these density functions to help us calculate the impact of consolidation on our water balance. And I apologize here, I'm keeping the screen zoomed in pretty substantially here to make sure that everything's visible. But because of that, I'm having to scroll up and down quite a bit. So I'm going to try and leave things right here where they are, but please just let me know, either raise your hand or ask a question, anything like that, if you'd like me to show anything that's up above. And real quick, I need to clear a message. Okay. Okay, so like I said, the next step, we're going to calculate losses. And really, we're going to calculate the entrainment loss. So in other words, this is the amount of water that stays entrained in our slurry after deposition. And because of consolidation, as well as because we're continuously depositing new slurry, that is going to be a rate. So it's not just going to be, a constant volume over time, right? There's actually going to be some rate of water that's lost to entrainment. And we'll calculate that now. The first thing we're going to calculate, though, is just the volume of water entrained in our impounded tailing or our impounded slurry at any given point in time. That's this equation down here. And again, it's based on those relationships on your handout. I'm not going to solve for it in front of everybody, but if you look at those relationships, you could get to this equation yourself. So insert a new expression element. And this time, we are going to call this entrained water volume. Now, it's certainly always good practice to insert a description for every element you create. I'm not doing that now for the sake of time, but it is something that I highly recommend doing to anybody who's developing a water balance model that's any more complicated than this. it really helps you keep from getting lost in your own model. But back to our equation, or excuse me, we need our display units first. So this is going to be units of volume. I'm just going to give it units of cubic meters. Again, GoldSim is dimensionally aware, so it doesn't really matter what units I give it, unless it matters to me what units I see it in. And we're going to see it in units of cubic meters. All right, so this equation, our total volume, that is equal to our total impounded volume, that's VT, times a quantity of 1 minus, and I'm going to use this element density in model. Up above, that's that selector element, the one that we've used to pick which density curve we're going to apply. So I'm going to be sure and use that one here. 1 minus density divided by a new quantity, which is specific gravity of solids, GS, times density of water. Okay. This expression element now is calculating for us at any given point in time, or for any time step, the volume of water that's entrained. To convert this to a rate, like I mentioned before, the rate of entrainment loss, we're going to compare the volume of entrained water at the current time step to the volume of entrained water at the previous time step. And the difference between those two divided by the length of our time step, that gives us our rate. So that's exactly what we're going to do here. To do that in GoldSim, the easiest way is to use a previous value element. We'll go in here and I'm going to label this previous entrained water volume. And this is also going to be in units of cubic meters because it's basically the exact same as the entrained water volume, just lagging by 1 time step. And our reference is going to be that calculation we made previously, entrained water volume. Initial value, this is the value that's going to be reported by our new element here at the first time step. Because at the first time step, there was no previous time step. So that's why we have to give it an initial value. We're going to leave it at 0. That's fine for our case. And then finally, we're going to go in here and calculate our entrainment loss. And that's going to be simply, well, and we'll give this a unit equivalent to a volumetric rate. All right, so this is going to simply be the difference between entrained water at the current step and the entrained water at the previous step divided by the length of time between the two. So we'll calculate that as entrained water volume minus previous entrained water volume. Divide that by, we're going to use a GoldSim model property called time, and this is difficult because it doesn't pop up automatically, time step length. There we go. So we know that we manually defined this model to have a time step of 1 day. So we could replace this, which is a constant value of 1 day. But within GoldSim, it's important to understand that there's the possibility that GoldSim could subdivide certain time steps into smaller time lengths. And in that case, if we just had a constant value here, we would actually mess up our calculation because we'd be looking at the difference in volumes up here across, let's say, 2 hours, but we're calculating it based on 1 full day. So that would obviously mess up our calculation. In this simple model, that's probably not likely that GoldSim is going to subdivide time steps. But in my opinion, it's always best practice to use these model properties whenever you can. So I always do that. And at any rate, that's just a simple explanation why I'm using this instead of just specifying 1 day. All right, and so that is all that we need to do to calculate our entrainment loss. Now this loss, like I said, is represented as a rate, which is exactly what we want for our water balance. The only other loss that we need to calculate now is our evaporation. And I'm going to come back and talk more about entrainment in just a moment, but I just would like to finish this set of calculations first. So our evaporation loss, that's going to be a function of, let's say, a pan evaporation rate. Now, that's something that may have been measured at a nearby climate station, something that may have come from some other type of general hydrologic calculations, something like that. And there's different ways to represent this evaporation rate. This is certainly the simplest, potentially the least accurate, but for the sake of these water balances, this is actually pretty consistent. It's actually yielded some pretty good results for us in the past. So we're going to continue using it. And our evaporation is also going to be a function of this pan evaporation factor. So if you're familiar with hydrology and evaporation calculations, typically we take a pan evaporation rate and reduce it slightly to account for actual conditions that are not quite the same as the idealized conditions within an evaporation pan. So I've brought this in. I think I use a value of 0.8, just a generic number, and a pan evaporation rate, I think I assume like 5 millimeters per day. So decently high evaporation. All right, so with that, we're going to calculate evaporation as our pan evaporation rate pan evaporation rate multiplied by our pan factor. And now here's something interesting. This gives us a linear rate, say meters per day of evaporation. To estimate actual evaporation for our impoundment in terms of a volumetric rate, we need to know the impoundment area. So as I mentioned during the PowerPoint presentation, we can do an area volume curve, or excuse me, an elevation volume curve. And we can also develop an elevation area curve in terms of our stage storage. And so that's what we've done here. The same analysis that was used to develop the stage storage curve that we showed above, that we used above here for these volumetric calculations, we use that same analysis to develop an area curve, and that's what we're going to use here. And so impoundment, elevation area, these are developed in terms of a lookup table. And so I'm going to give it the input of our height of the slurry surface. And let's see, oh, I never defined a display unit. This is going to also have a unit of volumetric flow. I also never named it, got ahead of myself a little bit here. So we'll call this our evaporation loss. And there we go. From this point, now we've already calculated our inflow, assuming no precipitation. We've calculated our two outflows, assuming no bank storage. And finally, we're going to come over here and calculate our net reclaim. Again, this will be a volumetric flow, and it is simply the difference between our inflows and our losses. So water in whole tailing minus entrainment loss minus evaporation loss. And there we go. Okay, and that, for this simplified scenario, that's all there is to it. I like to identify our key elements just to help someone else who's coming in after the fact and maybe has to deal with my model, make it a little bit easier for them to understand what our final output is. All right, so we've got ourselves a model. One other thing I'll point out quickly before running is that I've set up a few scenarios in GoldSim. So this is a very handy tool if you're trying to compare different options, different inputs, and their effect on the model. So I've got one scenario set up at 100,000 tons per day, 150,000 tons per day, and then a third scenario in which we're looking at 150,000 tons per day, but with a constant density. To show you what I've done, and if you're new to GoldSim and haven't seen this before, I think if you take a look at the manual, this is explained very, very nicely. So essentially we have two elements here that are part of our scenario, right? And so for each scenario that we've defined here, each one of these three scenarios, we have the ability to define different inputs for these two. And you can select several more if you'd like, several more elements to be part of this. But again, all we need is this. So we have three scenarios set up, and then there's this live model out here. Live model is something that you can switch over to, make changes, things of that nature, without really affecting your scenario results. It's a little more complicated than that and a little more beneficial than that, but for the sake of time, that's kind of what it is. All right, so now instead of just running the model once, I'm going to run for all three of these scenarios. Again, this is the power of doing a GoldSim model, is now I have in one set of calculations result from three separate calculations, and that's something you can't really do in Excel. So this is very helpful for us. Oops, excuse me. Oh, and I forgot to add a result element. I don't think I can do that. Well, we'll try it. We're going to add a result element, our available reclaim. We're going to plot that. And yeah, it's showing up on my other screen, but I neglected to do this before I ran the model. So I'm going to exit out. I hit F4 to go back into edit mode, delete everything. And now F7 brings us into the scenario manager, run the model again. And now we should be able to look at a comparison here. Great. So this plot now is showing us the amount of reclaim that's available to us in liters per second for these three scenarios. One at 100,000 tons per day, using the appropriate density curve. One at 150,000 tons per day, again, using the appropriate density curve. And then a third sort of sensitivity case, looking at our production of 150,000 tons per day, but neglecting our consolidation analysis. Now we're just assuming a constant density of our impoundment. All right, and so you can see between the green line and the dashed green line, a fairly substantial difference. Cumulatively, over the life of this impoundment, that can add up quite a bit. So this is just intended to show you the fact that it's important that we do look at our densities and put the effort in ahead of time to develop an appropriate density curve before we jump into our water balance models. All right. So again, the purpose of this presentation and this model was to just give a high-level introduction to how we bring consolidation into a water balance. And this is the simple way that we do it. By bringing in a density curve that we've evaluated ahead of time, we use that to calculate our entrainment loss, right? Then, based on the differences between inflows and outflows in our impoundment, the water that is released from our slurry during consolidation is implicitly accounted for. Now, we don't have time right now, but another interesting thing that we could do is take this rate of solids production and turn it into a time series element and see what happens if over several points in time we, let's say, double the production or cut the production in half, or let's say we stop production. And what you'll see, if we stop production but we're using an actual density curve, you'll actually see this entrainment loss turn negative. And that is indicative of water that's actually being released. All right, but ultimately, again, the key point that I want to drive home, we're calculating our entrainment loss based on our consolidation properties, and then based on the rest of the water balance, we're implicitly accounting for the water released during consolidation. And so that is a very important point to make to understand this model. And the reason that we do it this way is because it's ultimately a lot simpler. This calculation is far more simple than if we're trying to account individually for entrained water and water released. So this just helps us to do that. All right, so we are butting up against the end of our time here, and I would like to now go over, I see some questions have come in. And our first question, does the presented formulation for calculating entrained loss lend itself to calculating consolidation water reporting to the pool after the end of operations? when there is no addition. It got cut off, but I assume it means with no additional inflow, something along those lines. And so the answer is yes. If we stop depositing tailing, this is actually, I think, answered it already. But when we stop depositing tailing, this entrainment loss is going to turn negative. And that is only so long as our density curve is still changing with time. You know, at some point, we kind of assume our density curve could reach a peak value and just stay constant with time. If that's the case, then the entrainment loss during a period of no deposition is going to go to zero. But if your density curve accounts for that stop in production and the continued consolidation, then yes, this calculation does lend itself to calculating the water release to the pool just solely by consolidation. But again, since this is calculated as a loss, it's going to come out as a negative, and so you'll have to handle that appropriately. Okay, next question, and thank you everybody for these questions. These are good. Appreciate your effort in developing the model. Poor water depletion due to consolidation will be at different rates depending on the age of the slurry tailing. There are two time series here, rate of slurry input, and 2, rate at which each layer depletes pore water. The easiest way to incorporate these two is to use a convolution integral, and that's absolutely right. A convolution integral is what we're trying to solve ultimately. We're just trying to solve it in a little bit simpler way. So the rest of this question. I have personally used convolution integral in a couple of mine tailing water balance models. Give a try to this approach too. Good luck. Yeah, thank you very much for that comment, and that's absolutely true. A convolution integral is a very, very good way to do this. The model that we've created here is really just a more simplified approach. So if anyone else out there is curious about a convolution integral, maybe we can chat later. Okay, next question. By increasing the density of tailing, this also produces water release. Is this included as an inflow? Yeah, good question. So this is where it gets a little bit complicated. Or really not complicated, it's not as intuitive as you might think. So, right, increasing the density does lead to water released. And that is implicitly accounted for in this entrainment loss calculation. So if let's say we have a density curve that spikes at some period of time. Okay, that's going to lead to a drastic reduction in the entrainment loss during that period of time. So really you could think of it as this entrainment loss is dependent upon the slope of our density curve. Not necessarily the absolute value, but the slope. And so, right, as our slope increases or our density spikes, yeah, this entrainment loss is going to be reduced. And really that's reflecting the fact that there's a substantial amount of water that's released. All right, and so you could even get to the point, again, where even during deposition, you could have a negative entrainment loss that would represent an actual inflow. And so I hope that answers your question. The short answer is yes, it is accounted for. That inflow is implicitly accounted for by calculating the entrainment loss. Okay, next question. Let's see, how's the type of soil in the surface impacted the conductivity during the lifetime of the slurry dam? I imagine rainfall could impact a lot of this water volume if nothing is leaving. Okay, so if I understand the question, I believe the question has to do with like desiccation of the surface. And if that's the case, then yes, desiccation on the surface is going to drastically reduce the amount of evaporation. And so I've created a pretty simplified model here with just a single evaporation calc. In a typical tailings impoundment, we will actually do a separate calculation for wet or saturated beach areas, for dry desiccated beach areas, as well as for areas covered by a reclaim pond. So this is just a very simple evaporation calc, but we could expand this out to account for those different evaporation areas. Yeah, that's an excellent question. And next up, Oh, yeah. Missed what is in the height of slurry surface expression. Is that using the elevation volume relationship for the basin? Yes, it is. So the height of slurry surface element is, yeah, it's just using this lookup table, which is our elevation volume curve. To give you a snapshot, I'll leave that open as I move on to the next question. Okay, next question. We are using higher densities for new tailings, but what about the density of the initial tailing? Can we change or update this? So if you're referring to initial tailing being tailing that's freshly deposited, then you could, but if so let me back up. When tailing is first deposited, it comes in at a much lower density, and immediately we assume in our calculation that it increases in density up to our average impoundment density according to that density curve. So that is a simplifying assumption, but it's also an appropriate assumption, because really what's happening is there's a sedimentation process where there's some immediate release of water as soon as this slurry is deposited in the impoundment. And so that is also implicitly accounted for in our consolidation model and really in our water balance model, right? So we're assuming that water or the slurry comes in with this amount of water entrained in it. Once it hits this impoundment, some of that water is lost to entrainment, and the rest, if it's not lost to evaporation, becomes available to reclaim. So that's kind of the process that we use. Again, simplified process, and you can expand these models as needed, but that's how we're treating it here. Okay, another question about real operations where measured estimated densities of the are often vary, sometimes increasing, other times reducing. Is still this model representative? All right, that is an excellent question. And that's something that I was hoping to touch on and ran out of time to touch on, which is calibration of these models. And so the answer is yes. This calculation method is still representative, but the tricky thing is, if your assumed density goes down, really that relates to kind of the opposite of consolidation, right? That relates to an expansion of the soil. So realistically, that's probably not happening, but the level of accuracy of surveys and things like that used to estimate the volume of tailing in the impoundment might be producing a small local effect like that. And so you will see that kind of effect, and you can definitely just bring that directly in. And even if the density does go down, this calculation is still going to remain valid. You'll see a small spike in entrainment loss, or potentially a big spike depending on how much the density changes, but you can certainly bring that in. And on that note, I do want to say there's a lot of uncertainty in a real life TSF and in a real life impoundment that's not captured in just this simplified model, or really in any kind of simple water balance model. So it's very important for these water balances to go through and calibrate regularly. And that's what made me think of this, is this question here, because density is one of those things that no matter how much effort we put into the numerical analysis, the lab testing, the material characterization, all of it, there's still so much uncertainty, and our density curve is often not quite the same as what we assume from the beginning. So if you've got an impoundment that's been operating for several years, you can use the back calculated density to help inform prediction of future density. And you can also include our back calculated density, or really it's the density that would be calculated from the measured volume of tailing in your impoundment, divided, or excuse me, the tons of tailing in your impoundment divided by the volume measured through surveys. And you can bring that into your model. And for the period of time where you have measured data, you can compare your water that was reclaimed to what your model is predicting. And maybe your evaporation assumptions need to change, like for instance, your pan evaporation factor, or perhaps your density curve needs to be updated. So things like that can certainly be done. And yes, again, to answer this question, yes, you can bring in a real density curve even with reductions in density. Okay. And next, for a new facility without a production record or a beach survey, what is your preferred method for partitioning wet dry beach versus pool for evaporation calculations? All right, that's another excellent question. If we do not have an existing operation to use as a baseline, then it comes down to some volumetric calculations. Okay, so for a new facility, a lot of times we will have developed a pilot scale crusher plant or a crusher facility. Okay, and the tailing that comes out of that, we can get some representative samples. That's about as close as we can get to a true sample of what's going to be coming in the future. And we can use that to estimate things like beach slope, material properties for consolidation, but really it's that beach slope. And then based on engineering design, typically a tailings impoundment is going to be designed so that it can also hold the PMF, the probable maximum flood. Okay, and so that a lot of times dictates the maximum allowable volume of a reclaim pond. And if we have a maximum pond volume, and we assume that it's going to be maintained, then we can look at our beach slope, we can look at the geometry of the foundation, we can use a three-dimensional CAD model and come up with a relatively reasonable area for our pond, okay? Wet versus dry beach, that's a little more challenging. And so that's something that we usually look at existing facilities as much as possible, but it depends on your deposition strategy. If you're depositing, you know, from a single point all the time, then there's probably going to be a little more dry beach out there. If you're depositing from perimeter points, depositing from the crest, you know, kind of depositing from all around your impoundment, then you might be minimizing or even eliminating that dry beach area. So unfortunately, that's something that you just kind of have to assume at the beginning. And admittedly, this is not my area of expertise. So I usually rely on others to help me with that type of thing. But as a general response, that I hope that helps. Okay, so next question. What is the most useful device used for moisture measurement in the storage facilities in order to obtain the water content in the impoundment? Now that's another good question. There's lots of options out there. There's TDR sensors, there's moisture sensors that can be installed. I don't know though about their applicability within the actual tailing. I've never done that before. There have been operations completed where we will actually sample the tailing. There's special barges that are available that you can actually get out onto the impoundment. And I mean, sometimes depending on the level of consolidation, rate of deposition, you might even just be able to develop a roadway out onto that impoundment. Again, I would think that's a pretty unique case, but I've seen it done. Then from there, you can sample by SPT, you can sample by grab samples, you could really do what you need to do to get those samples. But ultimately, the short answer from my limited experience in this area is that sampling is a preferred option. Okay, next question. Calibration of the water balance is, as you suggest, essential. Have CPG-induced consolidation testing and Condis predictions been compared to actual experience? And yes, they have. And for the most part, they line up fairly well. The difference can come in, well, there's a few ways the difference can come in. You know, if we perform a seepage-induced consolidation test to get material properties, that test is on a very small sample. Okay, and it's also a test that's conducted on a sample from one point in time. Now, in any mining operation, the ore has the ability to change with time, just as new geologic units are encountered in the pit or in the underground operations, what have you. So changes in those material properties could lead to the changes in actual consolidation behavior of your impoundment. The other thing is, you know, some of your deposition could lead to segregation. And so the segregated material might have different properties. So certain aspects of your impoundment might consolidate at different rates than others, even though when you did your modeling with Condis, let's say, you assumed it was all one homogeneous material. And, you know, of course, as with any numerical code, with any lab test, there's limitations on how accurate we can get, because for the test and the model to be perfectly accurate, it has to perfectly represent the physical situation. And we're making some big simplifying assumptions with one-dimensional consolidation versus three-dimensional, and we're also making some big assumptions by breaking up an impoundment into columns and doing our consolidation analyses that way. So that in some cases, particularly for very steep impoundments with large topographic relief, that can introduce some error, and you may need to rethink how you're developing that density curve. But again, the short answer is typically yes. These predictions, they tend to line up well enough to use for an initial prediction. Again, as you say here as well, calibration of this model is essential. Comparison of actual measured densities to what you assumed for design, that is essential, because there's always a limitation on what we can do ahead of time to try and predict the behavior of these materials. Again, these are highly variable materials, and the behavior can at best be difficult to predict. All right, another question. If you are gaining water from consolidation, what is your preferred method to estimate whether that water is released to evaporation or to the pond? Okay, so that, again, in this model is being implicitly accounted for. So our evaporation loss, we assume that to be independent of, let's say, the amount of water being released from entrainment. And I think I see your point here. You're asking, of this water released by consolidation, how much of that is lost to evaporation versus how much goes to that reclaimed pond? Really, my preferred method, to be perfectly honest, is to not calculate that, because ultimately the goal is just to estimate our reclaim availability. Now, if you do for some reason need to calculate that, you could look at your drainage path. So this water released by consolidation is going to come up to the surface, right? And so that water is probably going to be evaporated from a wet beach area. So given that, you could use that to estimate, if our wet beach area accounts for 80% of our evaporation loss, then perhaps, I don't know, I'm kind of shooting off the hip here. I'm not suggesting this, I'm just saying you can consider this. You might be able to use your entrainment loss to calculate that, or excuse me, your evaporation loss to calculate that break. So yeah, sorry I can't be of more help with that one, but that's not something that we would typically look at. Appreciate the question though. Next question, have you seen geophysical measurements to obtain density estimates in 3D in place of your density curves? No, I've not seen geophysical measurements, but maybe what you mean is like a drone flyover or satellite LiDAR survey or something along those lines. And those, yes, there are limitations in accuracy, and so that has to be considered, particularly if you have a very flat beach slope. But those are available tools, and if you have a contractor who knows what they're doing with those tools, it could probably be quite helpful. And then next question, just to confirm, this method accounts for release of water from densified tailings in the lower layers due to consolidation from weight of new tailing. Yes, that's a very good point, and something that I neglected to say earlier. Yeah, the reason that we even see consolidation is because tailing that's deposited early on is loaded up as new tailing is deposited on top of it. So that new tailing loads up the old tailing, and that load is what drives consolidation of the lower tailing layers. All right, so every new layer of deposited tailing results in additional consolidation of the tailing below it. Excellent point. Okay, so I've gone a full 15 minutes over, and I apologize to everybody for that, but I hope that this was helpful, and I don't see any other questions coming in. So with that, I think I will turn it back over to Jason. And I just want to say thank you again to Jason and everyone at GoldSim. Thank you everyone for calling in today. We really appreciate your attention in this, and you've got my contact information on the handout. I'm always happy to discuss, answer questions, discuss interesting challenges. This is something that I really enjoy talking about. So with that, thanks Jason, and thanks everyone.
Thank you, Nick. That was a really good presentation, and we had a lot of questions, so I think a lot of people found it useful. Um, And I will be, like I said, this presentation was recorded, and I'll post it on our archive page. If you have any questions about how to get to that, you can send either myself or Nick an email. And like Nick said, feel free to ask either of us any questions, and we can answer those via email. And thanks again for joining in. We hope to see you next month. If you want to see what's coming up as far as future webinars and presentations, you can go to our webinars page on our website. And if you have any ideas for what you might want to see, I'm always open for new ideas. And also, if you want to contribute, like Nick has here, we also welcome that. So do please let us know. And thanks again, Nick, for all of your time. That was a really good presentation. So we'll go ahead and close up now, and see you next month. Thank you.